All right. So in lecture 9, I will talk about networks. It's not a very mathematical lecture. It is more a conceptual lecture. And then in lecture 10, I will do the nitty-gritty of the mathematics, so to say. Yeah. So the mathematics will be in lecture 10. And the conceptual introduction will be then in this lecture. Yeah. So what are we going to aim for in the remainder of this semester? We are going to develop network models of an economy based on the social division of labor. So we introduced the idea of a social division of labor, and I introduced very much the concepts of that related to that. We looked at the building blocks of that, commodities and consumer producers as representations of economic agents. Now we are going to put them together into some framework, and that framework is then a model of the social division of labor itself, and that is a network model. So we're putting these elements into a network model, and they will be represented through the network model. So if you see the network, you see the economy. You can derive from the network what the building blocks are for the economy, all the commodities that are involved, and all the economic agents, in particular the consumer producers. Yeah. So that is the main aim for today, to introduce that perspective. And what I will do is talk a little bit, first of all, about this representation. Is a network representation a kind of good one for a social division of labor? What we really do is use networks to represent, to flesh out, so to say, the trade infrastructure that emerges from the social division of labor. So we do not model the underlying social division of labor that much. We model the trade flows that come out of it. And so that is then determined by these different elements that we talked about, namely in the social division of labor, there are 3 types of commodities, for example, used. Those elements that are non-tradable, yeah, the resources that are non-tradable, and then intermediary goods that are tradable and consumables that are tradable. Yeah? And what will be modeled is only the stuff that is tradable. So from the beginning, I want to make that very clear. Only the stuff that is tradable will be mapped, as we can call that. Yeah. And that is essentially what we do. The network model that we will introduce of a social division of labor is essentially the stuff that we can observe, namely the commodities that are traded, the quantities that are traded, the prices at which trades happen, and so on. So that is what is in the network, essentially. Yeah. So we are essentially mapping an infrastructure. That is what it comes down to. And in those in that infrastructure, we have specialized entities, and they are in their specialization. So what I talked about last time, this increasing returns to specialization, that you have those corner points to the production set that is available to a certain economic agent, a certain consumer producer. What we have is that in that infrastructure, you occupy a certain profession, you occupy a certain corner point. Now, if you want to switch to another corner point, you essentially modify the trade infrastructure, because you will assume a different role, you will assume a different profession, that means a different production plan, and as a consequence, your trades will be different. And that means that when we map that, you are looking at a new map. The map is changing because somebody made a decision to switch from one corner point in the production set to another. So what follows when we look at those network models, they are snapshots because we do not take into account how these systems, the trade infrastructure changes when people switch from one corner point to another in their production sets. So when they exercise their abilities to change production plans, essentially. Yeah? So whatever follows, which is what we can call a directed trade network, or also, we refer to it as a production network. The network is a snapshot, and it is not representing the long-term development of the social division of labor. This requires a different type of theory. This requires a theory that takes one trade network into another over time. And we know that in reality, of course, these trade networks are in flux all the time. They're constantly adapting. That is not in the theory. So by choosing a network representation, we throw away something from that representation. Yeah? But what is represented then in a trade network, in a production network, to be more precise, is that we map all the supply chains in the economy, in the socioeconomic space that we consider, and we map them in all detail. And we assume that that is fixed. And of course, that how long it is fixed, that we do not know, but as such, it is a static representation. I want to emphasize it is a static representation of the economy. It's a snapshot. You make a picture of the economy at a certain moment in time. And what do you see? You see a production network. That is what I want to emphasize in these very first slides. Are there any questions so far about this? Right. So to set out the agenda for the coming lectures, production networks represent the trade flows, everything that is externalized. It is not mapping the resources that are used within production organizations that are not externalized, that are not traded. So if a farmer uses a piece of land that he or she owns, well, that owned land is not necessarily mapped. It is only the products that come from the land, the harvests that we have, that are mapped. Yeah. So the same holds for machinery. If you take a snapshot, when machinery is installed, yes, then it is part of the trade network. When it is part of the production organization, that machinery, and it is not changed, then it's not really necessarily part of that snapshot. Yeah. So that limits the scope of whatever next we do. Yeah. All economic agents are specialists. They are mapped in their specialization, and we map them using only the traded products, the traded goods that are related to their positions. Yeah? And that is it, essentially. Here's an example of a real life supply chain in the local economy. And this is, I showed this before in lecture 1, I believe. This is a local retailer selling apples, and all the flows of apples related to that retailer are mapped here. This is a snapshot. This was at a certain time in history, this was what occurred here in the local economy with regard to one retailer. Yeah? And the relationships related to this retailer with regard to apples, those are mapped. Yeah? Nothing else. And what is mapped is only what is traded. It is only what contracts are written for and flows that are occurring in this network. As you can see, the retailer, of course, has a shop. And in the shop, there are display units, and there are refrigerators and a freezing unit and whatever you have, cash register. All that stuff is not there because that is not traded at the snapshot that we have chosen, right? Even though a cash register is a tradable input, an intermediary good, in other words, in the social division of labor, it depends on the snapshot that you are mapping, whether that is the trade of a cash register is registered in the snapshot or not. So if you want to map the explicit purchasing of a cash register by the retailer from a factory, let's say, from also an office product distributor or some supply chain, that's a different picture. That's a totally different picture because it is related to a different time frame and a different set of commodities that we have here. So what this shows, this example shows, is that it depends on what you map. It is a choice what you map. And social division of labor is infinitely complex. If you want to do all ins and outs of the social division of labor, it becomes an extremely complex network that you cannot really truly grasp. And so what we do, we abstract away from a lot of things. So the cash register is gone from the picture. The refrigerators are gone. The retail unit is gone. Of course, when you map the financial flows, there will be rent payment or is mortgage payment related to these type of inputs. Of course, those can be mapped, but then they focus on the financial flows. Yeah, and that relates to banks and that relates to investors and all those kind of entities. Yeah. So what I want to make very clear from the beginning is that we determine the snapshot that we use, and the snapshot is incarnated as a network. It is entities that are connected by arrows that represent flows of goods, quantities of goods, and it is you who determines the scope and the framing, in particular the time framing of that representation. Yeah. Are there any questions with regard to that? Right. What are we going to do first? The first step is to talk about networks in general. What are those exactly and what can they do? Networks are a mathematical tool, and we are going to use them in a very particular way to map these snapshots of the social division of labor, those production networks. But we will first talk about general network theory. We first will set out the mathematical concepts of networks themselves before we are going to talk about production networks. And from the beginning, it should be made clear that networks consist of two things. Things that I call positions. A position in a network, well, a position is occupied by an entity, and that entity is usually an economic agent. It is a consumer producer. It can be a firm. It can be a government agency. Depends on what the scope is of your network, what the snapshot is that you're using to map the social division of labor. So These entities are the building blocks of the social division of labor, but they're also the building blocks of the network. Yeah? And then they are related to each other in a network. And that is the second element of a network, and those are links. And those links are binary only. It is between two positions, two entities in the network. So entity 1 and entity 2 are related. Well, how do we map that? It is mapped by a link, as we can call that. And we can hang information to these things as well. Huh? And the position is not an empty little thing. There's information there attached to the position. We will use that. We can name the entity that is in that position. We can describe what this entity is doing. And also the link carries information, of course. Usually it is traded quantities of goods that are attached to a link, because we are mapping essentially a trade network. Yeah. So to make clear the various names that are used to describe these things, in mathematics, they're called graphs. Now, graph is a kind of bad name, because graph we usually have for diagrams of demand and supply. Right? You graph your demand and supply. But the word graph came from when you write down a network, you essentially map the network on a piece of paper with those positions represented by nodes, and then the links are connecting these nodes. So that is where the name graph is coming from. Now, in the social sciences, these things we call networks, and we will stick to that here, of course. Yeah. Okay, so graph theory is very, very old, not ancient, but relatively old. It is already used in the 17th century and got a big boost in the 18th century, in particular, through the work of some mathematicians. And they invented this whole field of what is in mathematics called graph theory, and which we can call network theory. Now, in the 20th century only, in particular in the second half of the 20th century, social scientists started to use these networks to map social relationships. So sociology made a turn toward network theory to use this graph theory to do very specific things related to networks. Yeah. Now, this took an enormous boost in the 1990s. In particular, at the end of the 1990s, this field developed tremendously. And that was because physicists got involved. And since then, we can really talk about network science, because it has become a major tool, a major field that can be applied to many, many different things. And in the 2000s, in particular, this took off tremendously. So since the 1990s, we are using methods to describe very large social networks. And this is completely related to using computers and algorithms to describe these social networks and to map them and to determine the properties. So we are talking about large social networks, really large, millions of positions, millions of links. And it all started with the analysis of the World Wide Web, those pages on the internet and how they are related. And then physicists were interested in that because they got, they did grant proposals to apply physics methods to describe the World Wide Web. And they ended up revolutionizing network theory. And what they did is apply mainly statistical methods. And their specialty of statistical methods, namely mean field equations, to describe these networks. And they came up with insights that the social scientists never were able to derive, because they never tried to map these enormous networks. They did not really explore these networks using computers. So they did not detect these things, and they found some really interesting properties. And so network science, modern network science, is focusing a lot on these properties. And they are social network properties. The first one is that every social network has a scale-free architecture, as we can call it, also called topology. We will come to that. The scale-free architecture is that if you look at the connectivity of nodes with each other in the network, or these positions and how they are connected with each other, you get hubs and you get essentially endpoints with enormous numbers of weakly connected positions, entities, economic agents that have few connections. It doesn't matter what we are describing. We have, in the social networks, we have always huge numbers of very weakly connected nodes. And then we have a few extremely highly connected hubs, as we can call them, like Google, like Facebook on the internet. Yeah. So when you map the World Wide Web now today, and you see Facebook as a certain website, and you see Google as a website, and how they are connected to users and to other websites, news websites, for example, you see that they are very well connected. They are so highly connected that you can call them hubs. And Google, of course, the search engine of Google is deliberately built as a hub, because they want to collect all the information of everybody on the World Wide Web, essentially. Yeah. So scale freeness refers to a statistical property, namely of the degree distribution, as it is called, and that is a scale-free distribution. Yeah, it's not a normal distribution. It is a scale-free distribution. It satisfies what is called a power law, and also called an exponential distribution. Exponential distribution is an example of a power law, actually. And this is slightly more generalized. The second property that they found was that of a small world. A small world refers to the fact that you take two arbitrary positions and you can reach one position from the other by just a few steps in the network. So we have a very well connected network. So even though we do not maybe know everybody in China, you are on average only something like 4.5 steps away from an arbitrary person in China. Yeah? And this is a remarkable property of our global social network at the moment. And this degree of separation, as it's also called, is getting smaller. And there are a lot of social scientists now trying to investigate this and to map this more precisely and to do statistical analysis of social networks to find out what the degree of separation is of those networks. Then there is the property of assortative mixing. People that are alike, entities that are alike, they like to be linked with each other in the network. And that's exactly what is happening. We get communities in these networks, and they are formed how alike they are. And this is one of the issues, of course, that Facebook introduced. This became stronger. We already had it in cities when we were living in the days before the internet. You had your friends, and your friends looked like you, and you were mixing with them, so to say. Yeah. In Facebook, this is even stronger. You have many more connections with people in Facebook that you befriend, so to say, and this became stronger over time. Yeah. So we get community structures, and we get very intricate, interesting community structures that can be explored and mapped, and we get hierarchies of community structures even. Yeah. So all these social networks have a hierarchical structure, even when they are supposed to be flat, so to say. Yeah. Facebook is not intended as a hierarchy. Nevertheless, when you map the networks that are there in Facebook, you will see people that these normal relationships lead to hierarchies. Okay, all of these properties are social. They are not economic or socio-economic. They're social. And that is a kind of problem. When we map production networks, we will not necessarily see these properties. And also production networks are not necessarily large, right? They are large enough, but when they get really large, we have a problem. They need to be manageable, otherwise you lose oversight, especially with regard to supply chains. So I want to emphasize that when we talk about economics, these properties are not necessarily there. Because in economics, we talk about designed networks in some sense, not networks necessarily that are forming naturally from social interaction. Yeah. So connectedness, yes. Degrees of separation, yes, they are small, but they're not based on social context. They are based on trade. Of course, they're small. Yeah. Assertive mixing, yes, but again, because when you form a guild or you form an association with firms, you do that because everybody's producing the similar kind of products, right? So you have a guild of bakers in a medieval city, for example, a guild of carpenters. And they organize themselves in those guilds because they want to take power and control. Yeah, we will come back to that later when we talk about networks. Okay, so these properties are there in the economic networks, but they are not necessarily the most important. The most important is the trade flows. It is the design, in some sense, of these networks. Okay, let's first do some examples of social networks in particular. So I will talk about social networks for a few minutes. Here's, for example, a map of friendships at a club, a sports club, a karate club. And you have here all these members of the club. I think I believe that this is an American case. So these are teenagers or young people that engage with each other in the setting of that club. And you see here that you get this the scale freeness. We have two hubs, number 34 and number 1. They're clearly hubs here. And so this refers to that scale freeness of these social networks. So you have these popular people that people like to connect to. And these people can do a lot. They can bridge a lot of people, and they can play a very important role in these social structures. And they can also get power from that, of course. This is the ARPANET, which is the precursor to the internet, which is early 1970s we're talking about. It was set up by some corporations and universities. And you see it's a very sparse network. And this network is mapped on the geographical map of the United States. And you see here dedicated lines, telephone cable lines, cables essentially, that were dedicated to the ARPANET. So this was a very primitive internet, and it was supported by the military, and big grants were given to set this up. And it would, of course, the benefit would be going to the military, and they would be, it was a big project that was very wild, and they fully supported that in those days, those wild ideas. And it worked. We have now the internet, and we have all these benefits from it. And I'm teaching here at home and communicating to you through this internet. And it is all because in the 1970s, some idiots got money to do some weird stuff. Yeah. So here we have medieval trade networks, sea routes, and on land. And you see the various cities, the city economies, how they are connected with each other here. And this is again projected on the map of Europe. And you can make that into an abstract network, of course, with just positions with names, and those would be the city names, of course. And then cities are linked when there's a trade route from that city to another city. Romantic relationships in a high school, this is mapped as a network, an abstract network. And you see here all kinds of blobs. This is one feature as well of social networks, that you have a giant component, as it is called. So a giant component here is this here. Yeah, this is a giant component. And then you have these smaller components here. And you have very small components like this. And but the feature of social networks is always that you have giant components. Yeah, that's not necessarily the case with economic networks. What we normally have is only one component, because in a production network, we have our production systems are now so intricate that essentially everything is related to everything in those production networks. So the global economy is so interconnected with regard to production processes that everything is used for the production of everything, essentially. Yeah. Collaboration between researchers, that is another social network here. Again, the giant component shows up, and then you have two smaller components. You can map that. This is a standard way to link and to relate to scientists and how well they're doing. And you see also hubs appearing. This is a clear hub here. But you have also densely connected subnetworks, so to say. Here's a very densely connected network. So these are all natural features of networks. Here we have a real trade network in the Marseille fish market. Marseille fish market is a professional market where chefs and restaurant owners and hotel owners and retail shops owners are all coming in the morning to buy fish from fishermen. And here we have the trades that are occurring in that market. So it's a real market hall where the fish is displayed. People come and they will buy quantities of this displayed fish. And the green blobs are traders, sellers of the fish, and the little red dots are buyers of fish. And as you can see, the size of the blob is the revenue that is generated in the market by these sellers, essentially. Yeah. Okay, so what I want to do is, it's a good moment after 35 minutes or so have a short break and to have a breath of air, so to say, for a few minutes. Let's come back after at 40 after the hour. Yeah. All right. So these examples, they're great. They show network theory in action, so to say, as a mapping tool. And what I want to emphasize is that networks are mathematical concepts, and they're not quantified. They are a different type of mathematics, of course. It is a categorical kind of mathematics. That is how we are going to use them. Yeah? All right, so like I said, every network consists of two elements, something I call positions. Those are the entities that are connected. We saw them in these examples. Those can be persons, those can be websites, those could be traders, sellers and buyers. It depends on the context in which you use these networks. So in an abstract fashion, you call them positions, but they are occupied. And what is important is the occupier, so to say, of these positions. And the second element is those relationships, binary relationships only, links. If you want to describe different type of relationships, namely group relationships or that you form clubs or something like that, that's also possible, but that is not part of network theory. Those things are called hypergraphs in mathematics, and there's a whole theory about them as well. And those are more club structures or coalitional structures, we can call them. And those require a very different kind of analysis. For our purpose, namely to describe trade, the idea that you only use binary relationships is perfectly fine, right? You have two traders, a buyer and a seller usually, and that's all you need, right? We do not need more than that. Okay, what is very important with regard to network theory is that you can distinguish a directed relationship from an undirected relationship. So in a directed relationship, there is an inequality in some sense. You have a buyer and a seller. So the commodity flow, the traded quantity of a certain commodity, goes from the seller to the buyer. And when you look at the monetary flow, the financial flow, it's exactly the opposite. Namely, the buyer pays the seller for the commodities, of course. So there's a direction in this relationship, right? So it is not that one is the boss over the other. It can be a very different kind of directedness. When I look at a network of employment in an organization, in a firm, then the directedness is an employment relationship, right? You have a superior and a subordinate, and the superior has the authority to, for example, fire the subordinate. And so in the employment relationship, this directedness is totally different from the directedness in a trade relationship. You can also have undirected links. So undirected links are referring to that there is really equality when you have two friends, for example, right? A friendship relationship is an undirected relationship. Yeah. When you have collaboration between scientists, usually that is an undirected relationship. It is two collaborators working together on a research project. Yeah. So it's important that we can distinguish those. And if there's insufficient information of what exactly this relationship is, usually you use undirected links to describe those. In network theory, positions are completely abstract. They're like points in an abstract space, right? And we have to tell in our narrative with the network what exactly those are. And when you say, okay, these are employers and employees, right? That is totally different from the buyers and sellers in a trade network. Yeah, they're specialized entities in a social division of labor. Yeah, those are different things. And so the story that we tell with them is very important for economics. But in the mathematics, it's exactly the same thing. These positions are positions, and we can describe them by an abstract set, and we call that set A. So A is equal to a finite set of positions, 1 through n. Yeah? Okay. Okay. I referred to the mathematical tutorial that for the next discussion, A times A is very important. So A times A refers to the coordinated pairs A, B. And there's an ordering in the pairs, right? So A is first and B is second. Yeah, so A times A are all the possible combinations of two positions in A. Yeah? And there's an ordering. So A, B is different from B, A. Yeah? Because A precedes B in this coordinated pair. This is different from B preceding A. Yeah? When you have no ordering, you then usually use a set. So a set of two elements, A, B with curly brackets around it. That's a set of two elements. There is no ordering in that. However, there is ordering when you use these rounded brackets. Yeah. Any questions with regard to this? The second element of the network is this link. I will distinguish directed links from undirected links. The word link is always used for a directed relationship. So it is the pair A, B, where A precedes B. And you can also abbreviate that to simply writing AB. So AB from now on is the pair A, B, where A precedes B. So there's a direction. I go from A to B. And that's exactly how we interpret that. I go from position A to position B. That is described by AB. Yeah. So when I talk about trade, A is the seller, B is the buyer, AB is the flow of the traded commodity. So if B buys 2 units of two barrels of oil in the oil market from A, AB is then the trade relationship, and that is oil is shipped from A to B, and there are 2 barrels that make that journey. Yeah, and I can attach that to that link. I can put value 2 to that relationship AB. Yeah, that's how we can do it. Now, an edge, that is the word that I use for an undirected relationship. And an undirected relationship is that there is no precedence. A does not precede B and B does not precede A. A and B are equal. Now, how do we describe that? Well, we describe that by just combining link AB with link BA. And so I put that together into a set. So AB underlined is that both AB and BA are assumed to be there. So it's like a conversation. A says something to B and B says something to A. That's how you can interpret that. The flow of words from A to B, from B to A. That's a conversation. So a conversation is an undirected relationship, and it is represented by an edge. And this allows a stream of words to go from one to the other and from the other to the one. Yeah. Are there any questions about this? So this is a very fundamental point, right? We have a set of positions A. It's finite in principle. Right? We can count them 1, 2, 3, 4 till n. And then we can describe all the links between them. And we can, using this the same concept of link, we can also describe edges by having two links, the link AB and the link BA between two positions. Okay. So what do we have? Our building blocks now for network theory, for network science, is that we now have a set of all possible links that is called G sub A. G again is coming from graph. So G sub A is simply the set of all links that you are able to make in the set A. You take two arbitrary positions in the set A and you link them. And then you list all of these possible links. Yeah. Now, we can do the same for edges. Then I put a bar over it, because if I would put a bar under it, it becomes quite messy. So I put a bar over it. But when there's a bar, it refers to edges. And edges is that you go back and forth and you link them together, right? So it is A, B underlined for all arbitrary A and B. Now, what is now a network? A network is nothing but a bunch of links. That's what a network is. So a network consists in principle only of directed relationships. Yeah. So when I say network in general, when I use the word network, I mean a bunch of directed links between positions. And it is arbitrary. Now, we call a network undirected if every link is an edge. That means if the link AB is in the network, then the link BA also has to be in the network. Yeah? And so you can translate that to the property that every link is an edge. Yeah, is that clear? Any questions? An alternative way would be to say that G is a collection of edges. In other words, G is a subset of G bar A. Now, the space of all possible networks, we can call it a space. We can give that the capital G, G superscript A, because A determines the dimension of the space in principle. You see here is all possible networks that you can create on a particular set of positions A. Yeah. So this introduces a bunch of notation, I hope you will not be too confused by all these G's and the bars, but we will try to I will try to be clear when I explain these various formulations that we will encounter later on. Yeah. Okay. Now we have a network. A network is an arbitrary collection of links, as I said. Now the network can have an architecture or a topology. Now, what is a topology of a network? It is the underlying structure. And what is the underlying structure? Well, we want to throw away the directedness of these links. We will only want to map how the positions are linked, nothing else. No directedness, no flows. We throw away the flows. What is the underlying connected structure? That is essentially that you map the edges that correspond to those links. So you make every link an edge in some sense. That's exactly what I do here. Right? So the topology of G, T of G, is simply that you make every link in the network, AB, you make it an edge. And so it becomes part of this universal edge set. Yeah. Now you can also say, what is then the topology? It is simply that when there is a link, you make sure that the other direction of the link is also included. So you add to whatever link there is, you add the opposite link. Yeah. So the topology is that you just add more links, essentially. Yeah. So by now it should be clear that an edge is essentially a combination of two links, namely A, B, and B, A. A network is undirected if it is equal to its topology, because if it is undirected, there are only edges. And so there's nothing to add to those links. They all remain unaffected when you add the opposite link. So a network that only consists of edges is an undirected network that is equal to its topology. The space of networks has a certain dimension, namely it consists of 2 to the power n times n minus 1 networks. It's just a fact that I just list here. It's not important. And then the space of the undirected networks is simply all the networks that you can create from edges. And that is simply all the networks in GA, the network space, that has the property that the topology of the network is equal to the original network. Just some properties, they're not necessarily important. Yeah. Okay. The most important thing about networks, in some sense, is that we can so easily map them. It is essentially a mapping process, right? So networks can directly be drawn on a piece of paper. That is what the beauty of a network is. And so we get two-dimensional representations of those. Now, what we can do is represent positions by nodes, as I already said. Nodes is a small circle on a piece of paper with an empty space inside. And in that space, you can write a name. So you can name every node. And so you attach a property to every node. Yeah. So that's what I refer to here. And then what is a link? A link is A to B. A is now a blob. B is a blob. Yeah. Represented as nodes. I can draw an arrow from A to B. And when I have an edge, I can just draw a line without an arrowhead, so to say. Yeah? And so we get then a graph, and we saw them already in those examples, of course, right? You you map the nodes, you spread them out over the piece of paper that you have in a smart way, and then you draw these lines and arrows between those nodes. Yeah. Here we see an example of this at work. Here on the left, in blue, we have a network that consists of 4 positions, and we number them 1, 2, 3, 4. So they are named position 1, position 2, position 3, position 4. And we clearly see them where they are. Then all the relationships between those positions in this particular network are mapped by arrows. 1, 2 is in this network. I have an arrow from 1 to 2, but also 2, 1 is in this network. There's an arrow from 2 to 1. There is an arrow 3, 1. Yeah. So 3, 1 is in the network, but 1, 3 is not. 2, 3 is in the network, as you can see. 3, 4 is in the network, and 4, 3 is in the network. And that's it. There are no other relationships. So this network consists of 4 positions and 1, 2, 3, 4, 5, 6 links. Now, as you can see, when I map this, you see that this, between 1 and 2, there is a binary flow. It is one way and the other way. This refers to an edge. We can also represent that by a line. So the network in yellow is the same as this network here in blue, but we use, instead of those arrows, we use for some of those relationships a line, because those relationships are undirected. They are edges, as we call them. Are there any questions? What I want to express here is that the same network can be represented in multiple ways, depending on the tools that you use, whether you want to use arrows or lines also. Yeah. Formally speaking, from a theory point of view, those are exactly the same networks. And when you would write down a network, you would essentially write down the blue network. You would list all the links, and there would be 6 links that you need to list. So when you have a computer program describing the network, you need to use 6 links. Yeah. Let's apply that. And I apply it to the most simplistic network, real-life network, and that is ARPANET, because there's so few nodes, essentially. Here we have it mapped on the geography of the United States. However, you can make it purely abstract. So you can have an abstract network representation. And as you can see, all those links are, of course, undirected, because I can send data from one to the other. And it does not matter where I am, I can send that data. So the data flows are represented by edges. And that means we represent them by lines. And this is therefore an undirected network. And this is the topology as a consequence. Yeah. By the way, the previous example with the blue and the yellow network, the topology is just you delete in the yellow network, you delete the arrowheads, and you get only the undirected relationships underlying that topology. Yeah. Are there any questions about representing networks? Okay. Before we go in lecture 10, we go to apply network theory in a more general way to describe important economic properties of networks. I want to dwell still a little bit on the ultimate goal of all this, and that is to describe snapshots of the social division of labor, and namely everything that is traded and that is visible, mapping that out in a network, and we call that then the production network. Right. So what do we have then? It's a representation of a trade infrastructure in all regards. Now, what are the positions in the network? Those are the consumer producers, the economic agents, and in particular from their productive point of view. Right? We are not necessarily interested in these entities from what they consume. Yeah. So when we talk about a worker provides labor to a firm. A firm is also an entity. It's a position in the network. Well, that worker is a consumer as well, as a utility function, exercises demands on the consumption good markets. However, we abstract away from that in the production network, and we only will look at these entities from a productive point of view. So a worker is only a labor provider, yeah, as such. And so there is a flow coming from that entity, from that position of the worker, and that flow represents the hours of work that this worker is delivering to the firm at which this worker is employed. Yeah. Now the links represent those trade flows. So the positions are the entities, the firms, the specialized individuals, and they produce goods, whatever is tradable, right? And labor is one of them. It's an intermediary good, of course. And the trade flows are then represented by links, and those are directed in the production network. The flows are directed, and therefore the representations are links, not edges. Of course, we can talk about the topology of the production network, and then you replace all these links with edges, and then you see the raw structure of the production network. Yeah? And you can identify in that raw structure features that are important with regard to that network, and I will talk about that in particularly in week 7 when I talk about power in networks, and that comes from the topology. The topology helps us to identify who's controlling what in the network. Yeah. Again, I emphasize production networks are snapshots, right? This stands in contrast to the ultimate theory of the social division of labor, namely what also Adam Smith emphasized, and that is that it is fluid. When things change in the economy, when prices change, we will respond to that. And so we will change our production plans in response to what happens. If you have a profession and that profession is obsolete at some point because of production changes, right? Well, you better retrain yourself into something that is still useful, and that's exactly what we see around us, right? So as we speak, the COVID crisis really affects our economy, and it is shutting down a lot of activities. Retail is one of them. Being a shop assistant or a retail seller in a shop, well, at the moment you have no employee, and people might want to switch, and people are switching, right? There's an enormous boost of delivery services, for example, and lots of people are switching professions at the moment in response to that. So people are jumping into vans to deliver all kinds of packages from online ordering companies, Amazon, whatever you have. And that fluidity is totally missing in the production network. I do not map that. I don't have that. Right? So how flexible a production network is and how resilient it is in response to shocks, it is only partially described by the network that we use to represent that. There are elements missing, and that missing element is this adaptation. That is very important to realize. So I emphasize again what I started with, essentially. Okay. So I do not have, for example, this thing of equality of opportunity driving changes that you are able to respond to changes in the social division of labor in the production network. That's not in the production network itself. Yeah. Okay, so are there any questions with regard to the nature of networks and production networks in particular? Of course, we will come back to production networks in all detail over the next lectures. Yeah. This is just the beginning. I just set out here what is going on. Okay, so I talked about this already. Yeah, so in a production network, every consumer producer is giving a very specific productive role. He's sitting in a certain corner point of the production set that is chosen, that is fixed. And we are not talking about switching to another corner point of your production set in some sense. I emphasize that again. And a link from A to B is a trade flow from A to B, a producer from a production point of view. And the topology represents the underlying structure of the social division of labor and how positions in that social division of labor, the various professions, how they are linked. So, you know, a farmer producing meat delivers to a butcher. Well, that is a natural relationship. A farmer who keeps cattle is not necessarily delivering to a cloth manufacturing, so to say. Yeah, that would be nonsense. So these things are very well defined. This is totally different from a social network in principle, right? You define yourself by your profession, and that links you automatically in a certain way to other professions, and you get a very natural order in that production network that represents that. What I will be going to do over the next lectures, in particular the next lecture, which is in a few minutes essentially after our break, is to define topological properties, to look at flow structures in particular, connectivity as we call that. Yeah, that is very, very important. And the control of flows in the production network are very, very important. Who is in control of that flow? If you can control that flow, you have power, and as a consequence, you can extract from that additional benefits, rents, as we can call that in economics. Yeah? So rents from your position in the production network. And that is characteristic of a topology. And in particular, when we look at our contemporary platform economy, these platforms will show up as very specific entities in these production networks. And it becomes obvious from just looking at the topology of the network how these entities control. And so it is of interest to study that. So this is the next subject. The next subject is to describe connectivity, and we will start off with that in undirected networks in topologies, essentially. Yeah. So that is what is next. Okay, are there any questions at this time about this lecture? So this concludes this lecture. If there are not, what we will do is we have a 10-minute break or so, 5 to 25 after the hour. We will resume with lecture 10. Yeah, is that okay? Let's have a break, and I will set up the next lecture.